Good day, viewers. You're welcome to Science Spectrum with Don. You're welcome to a new broadcast of Chemistry Classic. Now, I would talk about stoichiometry, and basically I would tailor this lecture to balancing of chemical equations. Alright, so I hope you find it interesting. Let's proceed. So this is titled Stoichiometry, which is a quantitative relationship between the reactants, which are the starting substances, and the products of a chemical reaction. Then, under this, I'll talk about balancing chemical equations. Balancing chemical equations. Alright, so let's get started. Now, how do we pronounce the word stoichiometry? Stoichiometry or stoichiometry. So it's the relation between quantitative relation, because now we use numbers to show the relation between the starting substances that undergo a chemical reaction and what is formed, which we call the products, and that's our desired substance. Now let me start with balancing of chemical equations. Now, what is a chemical equation to start with? It's just a shorthand notation or a shorthand way of representing a chemical reaction, which oftentimes is caused by a chemical change. Right? So, a chemical equation is just a shorthand notation of representing a chemical reaction. Now, in a chemical reaction, you find starting substances, which are placed under some conditions. Take, for example, heat, light, etc., that forms or that goes to what we call the desired substances. The starting substances, we call these the reactants. You find them on the left-hand side. And of course, they undergo a reaction to form the products, which you find on the right-hand side. Products, reactant or reactant, substance or substances, as you like it. Yeah. So, let's now be more quantitative about this whole thing. Alright, so how do we balance chemical equations? Number one is this: you have to take something into account. The atoms you find on the left side, which we call the reactants, you also find on the right side. That's number one. Number two is there is no net change in the total mass of substances that undergoes a chemical reaction. So, in other words, the total mass of the starting substances would not be somewhat different from the total mass of the desired substances. In other words, they have to be the same. That describes the law of the conservation of mass. Alright, so having said this, another thing you may want to take into account is sticking in the physical states of those substances. Take, for example, are the substances solid? Are they liquid? Or are they dissolved in solution, which we call aqueous solutions? Solid, we use an S as a subscript. We use L for liquid, and of course we use AQ for aqueous solution. Now, how do starting substances proceed to form desired substances? One thing you may want to take note of is that atoms, molecules, and ions, which are the building blocks of matter, there are times they rearrange themselves in a spectacular manner. And when that happens, chemical bonds are broken and formed. And when this happens, you get desired substances. Alright, so I give an example of balancing of chemical equation. Let me take, first of all, the thermite reaction. And that's the reaction between aluminium solid dipped in or reacting with iron 3 oxide, and clearly when the atoms of these elements rearrange in a spectacular manner, a product is formed, which is on the right side. So that illustrates this. So what you find that the iron itself becomes dissolved. By the way, this is also solid. From the left hand side, these are solid materials. The iron gets dissolved, and of course what you have is aluminium oxide. So you have aluminium oxide. This is also solid, but the iron gets dissolved. So this we call thermite reaction. Now, if you look at the left side, which we call the reactant, and the right side, which we call the products, you find that the number of atoms on each of these elements are not the same. So what it means is that this reaction is unbalanced. Unbalanced, because the number of atoms you find on the left hand side must also be on the right. And of course, there shouldn't be any net change in the total mass of substances that undergoes this reaction. So the total mass we find on the left side must correspond to the total mass we find on the right. That is called the law of the conservation of mass. So let's now be more cognitive about this. So how to get this job done? Straightforward. Is this. First of all, I have the substances on the left, which we call the reactants, and I have the substances which I have on the right, which we call the products. So now I would name these elements. First of all, I have aluminium. It came out once on the left and on the right. Aluminum or aluminium. You find it on the left and on the right side. You also find iron on the left and on the right. These are elements, so I have iron. And of course I see oxygen also here on the left and also on the right. So we have oxygen. So these are the three elements that are represented in this chemical reaction. So how do we get the job done? Pretty straightforward. Now you ask yourself, how many aluminum do we have on the left side? There is a 1 here, oftentimes is not shown, and there is a 1 at the back. The 1 at the back, the coefficient represents number of moles, and the 1 represents the number of atoms. So this 1 times this gives us a 1, so I need not show that. So 1 times 1 is 1. So I have 1 aluminum on the left, and on the right you see there is a 2 down, the subscript, and of course there is a unit of 1 at the back, which is not shown. So 2 times 1 is 2. So I have 2 aluminum on the right. Now clearly they are not the same, and of course I have to make them the same. The same goes with iron. 2 times 1 at the back is a 2 on the left, and on the right is 1 times 1, that's a 1. Then we go to oxygen. 3 atoms of it times the coefficient at the back, which is not shown, which is 1, we assume. 3 times 1 is 1. So we have a 3 on the left, and on the right, 3 times 1 is also 3. Now if you look at this, the number of atoms of each of these elements, you find out that they are not the same in aluminium and iron. So what do? I have to make them equal. So I have to make aluminum 2, just like we have it on the right. So how do I make aluminum 2? I will insert a coefficient that the number at the back of either of these substances, right? And the goal is just to make them equal. So aluminum on the left is 1, on the right is 2. So I have to make aluminum on the right, on the left rather 2. So I will insert a coefficient at the back 2. So 1 times 2 makes aluminum 2 now on the right. So it's 2, 2, left 2, right 2. Now we go to iron. Iron is 2 on the left but 1 on the right. So I have to make iron 2 on the right. So I will also insert a coefficient right here. Please note you don't stick in the numbers here, it's always at the back. So now 1 times 2 makes iron 2 on the right side. Now clearly you see I have aluminum 2 on the left, 2 on the right. Iron 2 on the left, 2 on the right. Oxygen 3 on the left and 3 on the right. So the balanced chemical equation becomes 2 moles of aluminum plus 1 mole of iron 3 oxide, forming 2 moles of iron plus 1 mole of aluminium oxide. Now this is the balanced chemical equation. Now, I'll give another example. We want to beam this for a while. Alright, so take for instance, okay, for the sake of time, I may need to wrap it up here. I will proceed from here in our subsequent bulletins. Thank you.